So next, we're going to kind of look at these graphs to get a better feel for these logarithm functions. And so I'd mentioned earlier that they are just the inverse of an exponential function, and so you're actually looking at that take place right here. So if you remember when we did inverse functions, they are the reflection across the line y equals x, and so all these values have been interchanged, and so we can kind of take a little closer look at this. So if we look at this point right here, let's see, that's at 1, 1, 2, right? So, and here's your exponential function, right? So if x were to equal 1, 2 to the 1 power would equal 2, right? And so then right here at 2, you get 4, right? Because if you, 2 squared is 4, and we can look at one more. So if you look at this one, if you plug in 3, 2 to the 3rd power is going to give you an 8, right? And so on inverse functions, these values interchange, and so we can kind of look at that here. So let's kind of look at this point right here. So this point is at 2, 1 instead, right? So it swaps. So it's 2, 1. And so see what's going on here is see if x is 2. Remember, what this is asking you is 2 to what power gives me this guy right here, right? So 2 to what power gives me this? So 2 to the 1 power would give me 2, right? That's what x right here, see, that's 2. Let's try another point. So this point right here, if you plug in 4, you're going to get a 2, I'm sorry, 2. So if you plug in 4, you get a 2. And so if this is a 4 right here, this is saying 2 to what power gives me 4? And so the answer is 2. So that's why your y value is a 2. And we got one more point right here. So let's see, if x is 8, there we go, that one's going to be 3. Because if you put in 8 right here, it's saying 2 to what power gives me 8? 2 to the 3rd power gives me 8. And so you can see that all these points flip-flop. Okay? So let's look at some of the stuff about logarithm functions. So you can see that they're using a instead of b for right now for the base. But anyways, so that value's got to be greater than 1. Okay? And so it's continuous. It's 1 to 1. So since it's 1 to 1, that's by definition it has an inverse function. Okay. Now this is kind of what's interesting. So if you look back at our our exponential function, our domain was all real numbers, right? Domain was all real numbers from negative to positive infinity. But on the other hand, my range was just from 0 to infinity. Now remember, the x and y is flip-flop. So now what's going to happen is my domain is restricted to 0 to infinity. So it switches. Now my domain is from 0 to infinity, and you can tell by looking right here. Okay, and then you can see that the range actually encompasses all real numbers, negative to positive infinity. Also, we're going to have a vertical asymptote. Okay, so if you remember on the exponential, we had a horizontal asymptote. Now that's going to turn into a vertical asymptote. So it's going to flip-flop, and so the logarithm function is approaching, basically in this case, the y-axis, but this can shift depending on transformations, just like our horizontal could shift earlier when we graphed the exponential. Okay, but that'll help us graph this, so we're not having to find all these decimal values. We'll just probably focus on these nice numbers, transform them, and then use the vertical asymptote to help us draw our graph. And so if you look down here, this is just these are just the tables for the exponential function and then the logarithm function. And so you can take a little closer look at this if you want, but what you're going to notice is that they get interchanged, the x and y values. So let's go ahead and look at some transformations, and then that's what we're going to do with this graph. You can see right here to the right. So very similar transformations. Y'all should be familiar with these. So if you add or subtract to your log, it's going to cause you to shift up or down. Now if you're going to add or subtract directly to x, it's going to do the opposite of what you kind of initially think. You're like, oh yeah, if I add to x, my x values increase. Actually, we're going to shift to the left instead. Okay, so if you add to x, it actually causes a shift to the left. If you subtract, it's going to cause a shift to the right. And what that's also going to do is that's where your asymptote's going to basically line up. And so basically what you do is you take this and solve for x. So if you took this and solved for x, like set this equal to 0, you'd have x equals negative c. That's where your vertical asymptote would be in this case right here. Down here, if you were to set this equal to 0 and solve, you'd actually have it equal to positive c, right? And that would be the vertical asymptote in that case. So yes, it can shift. And then our reflections, so if we look here, if you multiply your log by -1, it's going to cause you to reflect about the x-axis, okay? And so basically what's going to happen is like all your positives become negative and all the negatives become positive. And basically whenever we did transformations like that, we wrote down multiply y by -1. That's basically the same thing as, it's synonymous with reflected across the x-axis. Then if you multiply the -1 directly to x, that's going to cause a reflection across the y-axis here, okay? Basically, you would multiply all your x values by -1, which would cause these all to reflect to the other side of the y-axis, okay? So what we're going to do is we're going to take this graph here. We're going to take a couple of these points. We can, you don't have to take a million points. We can actually just take 3 if y'all really want. That's fine. We're going to take these 3 points and we're going to transform them with these transformations down here. So let's see. This point right here is going to be at 1, 0. This point right here is at 2, 1. And this point right here is at 4, 2. Well, let's just make sure you understand where those came from. So if you were given this equation, could you actually come up with those points? And so what's going on here is 2 to what power would give you 1? 0, right? So what you could do is you could convert this to exponential form if you really wanted to kind of help you get your points if you really want to. A lot of people also, what they'll do is they'll interchange this here and graph the inverse function, which is the exponential, and then reflect it. It kind of seems like a lot of work. We're going to keep these fairly simple. So if you can kind of get the example going for you and then just use your transformations, you're going to see that all these down here are going to be base 2. So we're just going to take these 3 points and move them around. Okay, so our first transformation right here, so we're going to go ahead and use transformations to graph each function, include our asymptote, and then use the graph to determine the domain. Okay, so this first one you can see right here, this is going to cause us to shift to the left. We're going to go left 1. So we're going to take those points I have right there. So if you wanted to, you could kind of plot them there if you want, kind of lightly, and then all those points are just going to move to the left 1. So we're going to go left 1 here. I'll put those a little bolder now. Left 1 here, left 1 here. Now your vertical asymptote was originally the y-axis, but it's going to shift over 1. So my vertical asymptote is now at x equals -1. Okay. And so if you look back at the graph, you just need to draw that general shape right there, okay? So we're going to go ahead, as I go to the left, we'll go ahead and curve down towards the asymptote like that. And as I curve up, I'm just going to kind of go kind of slowly. And there you go. And so now if you're looking for your domain, the domain, let's see, it's going to back up all the way to -1, but not include it. So it's going to be from -1, and there is no limitation to the right, so we go to infinity. Okay, so I got one more of these here, and so what's going to be different about this is you got 1 plus the log base 2 of x. And you can leave it like this if you want, but you could rewrite it if you really wanted to as log base 2. And then what you'd want to do is put the x in parentheses and then put the +1, just to make sure it's absolutely clear that that 1's not getting added to the x. And that's part of the reason that they probably wrote it this way, was just to make sure there wasn't any confusion, that this is on its own right here. Okay, then that +1 is applied afterwards. And so that +1 would cause our graph to go up 1, right? So now that's what we're going to do with those points. Once again, I'm going to put the original ones there, just kind of lightly. And so they're all going to shift up 1 unit. Okay, so that means that my asymptote actually didn't change, so it's still going to be right here at x equals 0. And so once again, as I curve to the left, we'll go down and use that asymptote as guidance. And then as I go up to the right, just kind of go up and slowly to the right. So this domain for this one is not going to be any different than the example I was given. So let's see, the domain here is going to be from your vertical asymptote to the right. So it's going to be from 0 to infinity. Okay, so, but the base isn't always going to be 2. This is kind of an introduction. If you go ahead and take pre-cal, you're definitely going to go more in depth on these, but we do want to look at 2 special ones besides this one. Base 2 is kind of the easiest one to start with, to be honest. But let me go ahead and flip to the next page so we can look at what we're dealing with. So logarithm functions with base 10, these are going to be known as common log rhythmic functions. And so whenever you see base 10, you can actually just leave it off and just write log of x. And so if the base is not there, it's going to be understood as 10. And that's actually what your calculators are going to be defaulted to. So when you press the log key on your calculator, it's going to be defaulted to 10. The newer calculators will let you adjust those. They'll let you actually change the base if you want to, but the ones we're going to be working with, they're going to be defaulted to base 10. So not really too much different from the one we just got done doing. The only thing is the bigger your base gets, the kind of the slower it's going to rise. Okay, and the faster it's going to get to your vertical asymptote, or at least approach it. And so that's kind of what's going to happen. And so if you once again, if you were to convert this back to exponential form, what this is 10 to the power of y equals x. And so you can see that if x is 10, then y would have to be a 1 right there, right? And then if let's see, if x were 1. If x were a 1, that would have to default to a 0. Okay, and so then they found one that was a little messy, just so that they could pick up an extra point here. And so they went ahead and plugged in 5 for x. Okay, and so this would be something that you'd have to put in your calculator. And actually, I'll just go ahead and show you real quick since I have mine pulled up. So you can actually type in the log keys right next to the number 7. So if you type in log, you can actually type in the number 5. And press enter, and there you go. So 0.6989, whatever, they rounded it to 0.7. And so like I said, long ago you would have to look in a index to figure out that value right there, but your calculator is got the index basically stored in it, so you can just type it in and it'll do the work for you. Okay, so what we'll do is we're going to do a transformation with this one just to practice our transformations again, and just be like the previous page. And then we're going to look at the natural log, and so we'll look at that in just a second. So let's go ahead, and I'm going to complete number 60 down here real quick. So what I'm going to do, let's see, I'm going to go ahead and take those points right there. So I'm going to go ahead and put them there. So let's see, 1, 0. At 5, I was at 0.7, so about right there is fine. And then let's see, at 10, I was at 1. So like I said, that thing's going to be, rising at a much slower pace, but nevertheless, it's rising. Okay, so once again, we've got a shift here. This one, it looks like we're going to go to the right. Looks like we're going to go to the right 2. Okay, so that's going to cause this guy to go to the right 2, to the right 2, and then, yeah, I'm going to go a little off the graph, but that's fine, whatever. Okay, so my vertical asymptote shifts also. So originally it was right here at x equals 0, so now it's going to be at x equals 2. So we're at x equals 2. Okay, so this guy is going to sharply go towards my asymptote, and this guy is going to do the opposite. It's going to rise really slowly, right? So not the prettiest graph, but try to make it with a curve. Mine's not great, but I'm in the right spot. Okay. Okay, so that's for base 10 right here. All right, so now we're going to go back and we're going to look at natural logs, and we've talked about E, okay? So if you have base E, there's a default for that, and there's a shorthand, ln. And once again, that's in your calculator, so if you look right there, it's a below log, so ln, and then you can type in values, and so like here they've typed in 3. If you type in 3, the natural log of 3 is basically 1.1. So they rounded it for us, okay? So we'll scroll down and look at this a little bit closer. So we will use natural log quite a bit in the next couple sections, okay? The good news is actually this is going to be the last part of our graphing though. So we're not going to be graphing after this example right here. So let's see, we got our point right here at 1, 0, because either way, you know, because this converts right here to e to the power of y equals x. And so if x is 1, well then my power must be 0, right? So anything raised to 0 is going to equal 1 as long as my base isn't 0. Okay, and then they kept it pretty simple for us. They just plugged in 2 and 3, and that's fine. So if you were to do a 2, okay, so if you were to plug in natural log of 2, you would get about 0.7 right there. If you plug in natural log of 3, you get about 1.1. And so we'll go ahead and just use those 3 points right here and do our transformation here. Now this one down here is going to have a little bit more going on, but I think we'll be okay. I'm going to go ahead and plot those points before I forget. So let's see, we got 1 right there at 1, 0, and then at 2 we were at 0.7, and then at 3 we were at 1.1. Okay, so we got to transform those 3 points and that vertical asymptote right here, which actually it looks like it's going to stay where it's at. But okay, so if you want to, you can leave it like this, or you can look at this as being negative natural log of x, and then that's a positive 1, so plus 1, right? Vertical transformations we'll want to do last, so we need to do this reflection first, okay? So this is going to cause a reflection across the x-axis, okay? And so if you want to, basically, you can also just write, you know, basically we're going to multiply y by -1. That's how that reflection is going to occur. And then, because of the plus 1, we'll go ahead and go up 1 after that. Okay, so when you multiply y by -1 on that first point, that doesn't change the where the point's at, because y is already 0, so 0 times -1, but then it goes up 1, so it's going to go right there. Okay, so then this next one, it was at 0.7, okay, so then it gets multiplied by -1, okay, so now it's at -0.7, and then it goes up 1 unit, so that would actually put it at positive 0.3, so this is, hopefully you're following me here. So if you were to look back on the, here I'll mark it right here, so that was at 0.7, right? So if you, oops, it's ugly. If you multiply 0.7, if you multiply 0.7 by -1, it turns into -0.7. Then if you add 1 to that, if you go up 1, add 1 to it, it goes up to a positive 0.3, and so that's how I ended up here. Now my other one's at -1.1. So if I multiply by -1, I go to -1.1. And then if I rise back up 1 unit, then I end up at only being at -0.1. Okay? All right, so my vertical asymptote did not change. So let's see, I'll do that in red. Okay, so that's still going to be at x equals 0, okay? So now when I connect my dots, so it reflected across the x-axis, so if you look at the original one, it's going like this, so now it's going to actually come down like this instead. It's going to come down. Okay, so I'm going to follow kind of the asymptote down and then just do the best I can to make it look decent. And then it goes up like that one. So that one was a little challenging. Domain should be pretty simple. Domain should just be from 0 to infinity. So the domain is going to be from 0 to infinity. There you go. Okay, so I have one more thing I wanted to look at on this page right here, and that's just finding the domain of the logarithm function without the graph being given. But we've actually kind of already talked about this. It's pretty simple. All you're going to do is you're just going to take this, and my hint basically is that logarithms can only be evaluated at positive values. So this has to stay positive right there. That's your, hence that's your domain. What x values are going to keep this parentheses positive? So you just take x plus 4 and you say, okay, well, what's going to make that greater than 0? You know, that, there you go. Whatever values make this stay positive, that's your domain. Okay, and you can see that if you were to look at transformations, this would transform to the left 4, right? And your vertical asymptote would be at -4, and your domain would be from -4 to infinity, and that's exactly what this is going to be. So we'll go ahead and subtract by 4 on both sides. So let's see, we're going to get x is greater than -4 as your domain. But once again, we'll want to go ahead and put that in interval notation. So from -4 to infinity. There you go. Oops, there we go. The next one, I mean, very similar. We're going to test your inequality skills if you remember all those properties. So we'll go ahead and take 2 minus x, set that greater than or equal to 0, right? Because that's what we need to keep these values when you evaluate your logs. Got to be positive in here, okay? Couple different ways you could solve this, and so I'm going to solve it this way just so I can review this property of inequalities, make sure we don't forget about this. Because what's going to happen here is I subtracted by 2, but now I'm going to divide both sides by -1. That's going to cause my x to become positive, but this is interesting. What happens is this inequality is going to reverse from being greater than to a less than. And so then -2 divided by -1 becomes +2, but you got to make sure you switch your inequality sign. And by the way, that would cause a reflection across the y-axis, right? So if you were to go back up to these graphs real quick, what would happen is this graph would end up going the other direction, right? And so that's going to be reflected here on your domain. Your domain is all values less than 2, so that's actually going to be from -infinity to 2 right there. Oh. All right, and so that'll be it for this part. I'm going to make part 3, and that'll be it.